Okay, in this video we're going to talk about Unit 11, Objective 2, the ratio test. So let's just jump in, get the ratio test, and do a real quick example. So let's say, suppose you have a series and we'll call that series A of n. Then we want to let some limit as n approaches infinity of the absolute value of a of n plus 1 over a of n equals some value L for limit. Now, if L is less than 1, your series is going to converge. If L is greater than 1, your series is going to diverge. And if your limit L equals 1, the test is inconclusive. And we'll have to find another way to do this problem. Now, we can use our ratio test on pretty much any series that you want. Most of the time we're going to end up with L being greater than or less than 1, so we're not going to have to worry about an inconclusive answer. But sometimes we'll get that and we'll have to fall back on our comparison test, our p-series, our limit comparison, an alternating series, which we haven't looked at yet, or geometric series. But this is a pretty good one to go after. Most of the time, the test will not be inconclusive. So like I said, this is going to be a good one to try from the beginning. It's a little bit messy, but it's going to get us answers a little bit easier than the limit comparison test, and we're going to be able to use it pretty much every time. So let's take a look at an example. Let's try to find if this series is going to converge or not. So let's say the series of negative 10 to the n power divided by 4 to the 2n plus 1 times n plus 1 power as n goes from 1 to infinity. So we can kind of see that this is going to be, the ratio test is going to be better than the limit comparison test. I'm not really sure what we would call our b sub n here. So ratio test is going to be a very useful one. But like I said, it's going to be a little messy at times. So what we want to do is we want to think about what we need for the ratio test. We need a sub n, which we have, negative 10 to the n power over 4 plus 2n to the first power times n plus 1. But we also need a of n minus 1. So how we're going to find that is we're going to take, n plus 1. We're going to take n plus 1 and we're going to put it everywhere we see an n in our original problem. So a of n plus 1 is going to be negative 10 to the n plus 1 power over 4 times 2, 4 to the 2 times n plus 1 plus 1 power times n plus 1 plus 1. So everywhere we had an n is now an n plus 1. So let's go ahead and simplify this a little bit. So distribute your 2 in the power of 4. You're going to get 2n plus 2 and then plus another 1. So we're going to get 4 to the 2n plus 3. n plus 1 is going to be n plus 2. And we just have a negative 10 to the n plus 1 power. So there's our n plus 1. So now we want to take the limit as n approaches infinity of that a of n plus 1 and we want to divide that by, and we want to take the absolute value of all this, Divide that by our original a of n, which means we're going to multiply by the reciprocal. So that's the limit we want to take. Now, not everything, a lot of the things that we have here are going to cancel out, and this isn't going to look as gross. If we have 4 to the 2n plus 1 over 4 to the 2n plus 3. Now notice that everything here is multiplied, so we can just go ahead and start canceling things out. If we think about just the 4's for a second, so if we had 4 to the 2n plus 1 over 4 to the 2n plus 3. If we have the same base, all we have to do is subtract our exponents if we're dividing. So 2n plus 1 minus 2n plus 3 would be 4 to the negative second power, or just a 4 squared in our denominator. So we can get rid of that, and replace it with a 4 squared. Similarly, if we look at negative 10 to the n plus 1 and negative 10 to the n, that's going to go away, and we're going to replace it with just a negative 10. We can't cancel out the n plus 1 and the n plus 2, but we've gotten rid of a lot of stuff. So if we look at what we have now, we have the absolute value of negative 10 over 4 squared, or 16, times n plus 1 over n plus 2. Now we can take that negative 10 over 16 out, and since we can take the absolute value, let's just call it 10 over 16, times the limit as n approaches infinity of n plus 1 over n plus 2. If we take that limit horizontal asymptotes, we have a power is the same, 1 divided by 1. So the limit itself is 1. So this whole thing equals 10/16. 10/16 is less than 1, so our series is going to converge. So this is one that we're going to be able to use quite a bit. It's one that AP is going to have us use quite a bit. Especially if we have to find something called a radius of convergence, which is going to be the next video. So this is one that we really need to know how to do. We'll be able to use this one, like I said, on just about every series. Every so often we're going to get one of these limits that equals 1, and we'll have to fall back on another test. But this can be our go-to as long as you're all right with all of the messy work that can happen. So we'll call it quits on this video, and we'll see you in the next one.